Okay, so this is the fifth asynchronous session. Um, at this point, we should have just met on the 15th of July. So we're going to look at how do we do discrete probability distributions. All right, so this is starting to move us toward the idea of inferential statistics. We're going to use some of the basics that we learned in probability last time around and start to try to be able to turn this kind of inside out. And you'll start seeing some of the statistic language coming back into this. So the first thing we have is what we call a random variable, which is usually marked by some capital letter X. So this is like a container, and into this container you can put in certain values that represent the outcomes of a procedure. Okay, so you do a procedure, this is a possible outcome that can be in there. So like, let's say you are holding an election, and we have two possible candidates, one Trump, one Biden, and here the X can contain either Trump or Biden. Or you have like a baseball game, right? And the number of outs that a pitcher gets before he has to leave the game is usually between like 1 and 27. So these are values that can go into this random variable. A probability distribution is some sort of description where you put values into the random variable and out comes probabilities for those values. So those probabilities tend to be, they're directly associated with the values that you put into the random variable. If it's a discrete probability distribution, then these values are numeric, and they're either finite or they're countable. It doesn't have to be finite, but it must be countable. So there is a finite number of values, or they have to be countable. If it is, so countable means you can make a mapping to the real numbers. So like you could have a first value, a second value, a third value. They don't have to be 1, 2, 3, but there has to be a way to count the values. The other possibility is that it's continuous, and there the random variable is still numeric. So this is discrete. The random variable is still numeric, but now it is infinite and non-countable. So like if X can take the possibility of various weights like pounds or heights, things like that, there's an infinite number of possible weights a person can have, and those weights are non-countable. You can't map them to the counting numbers. So this is like the basic language that centers probability distributions. If I have a probability distribution, there's certain requirements that have to be made. So remember that the probability distribution takes a value for the random variable, right? So some value, and returns a probability for that value. Right, so it sticks that value into X and then returns a probability for X. So this means that if you add up all the possible values, so you take the sum of all the possible values, you should get 1, right? The probabilities of the sums, of all of these, so the sum of the probabilities should be 1, right? So it's not adding up all the values, it's the sum of the probabilities of the values. So let's rewrite that a little more neatly. So if I take the sum of all the possible values for X, I should get 1, right? They also have an idea that each of the possible values has to be between 1 and 0 inclusive, right? So you can't have like one of the values has a 2 and one of them has a -3. That doesn't make sense. So if you have this and it's associated to a procedure and its events, then you have a probability distribution. And if you look, I gave an example like in the notes here of like, here's a simple probability distribution where this is the possible values of X. Wow, that's not right. That has to get changed because that should be 0, 1, and 2 in 2 births, right? The number of girls in 2 births should be 0, 1, or 2. So I'll fix that in the notes. There we go. And in the end, the probability of having no girls is 25%. The probability of having 1 girl is 50%. The probability of having 2 girls is 25%. And you can like work with Punnett squares to prove that. And ultimately, so we have a thing here with all the probabilities add up to 1. They're all between 0 and 1. And these are the events that pertain to a particular procedure. Now, not all probability distributions can be written in tables. Sometimes you need an equation or you need some other descriptor. It's like just like functions. Tables are one ways of describing them. But like this can be, we'll see later on in this that the Poisson distribution cannot be written as a table because there is an infinite number of possible values for the X here. So I'm going to fix that in the notes in a little bit, but yeah, that should be no girls, 1 girl, or 2. You cannot have 3 girls and 2 births. All right, so so we go into ways to represent probability distributions. This is like we just saw here. One is a tail. We flip 3 coins. Now you can have 0, 1, 2, or 3. Possible heads is the outcomes. These are the probabilities that are associated with that. So that's one way to describe it, is using a table. You could turn that table into a histogram, but sometimes you just have to use like a formula or something else. I mean, it can be presented in a lot of different ways, but it has to have those characteristics in order to be a probability distribution, yeah? All right, so the next thing we get here are what are called parameters. And probability distributions have 2 major parameters that we worry about. And one is the mean of the probability distribution, and one is its standard deviation. And this is how we're going to end up using that with some of our rules on normal distributions and things like this, is where we're going to start getting into some inferential statistics. Mean is just exactly like we did a weighted mean back when we were doing descriptive statistics. So literally, like if this is my probability distribution and I want the mean, I treat it like I'm creating a weighted mean. I put the, so I go stat edit, I put the values in L1, and then I put the probabilities, in L2, Okay, and you can check that those probabilities are going to add up to 1. They do. This happens to be a binomial distribution, but we're not going to get into that. All right, so we go we go back to the main screen. We go stat calc, there we go. The one variable statistics, we're going to do it on list 1. The frequency now is list 2, so you got to make sure you plug that in there. We calculate, and it tells me that the mean of this probability distribution is 2. It also gives me the standard deviation, and I have formulas here for the mean and standard deviation. They do follow the same formulas. It's as you would for a population. Notice that this is a population, right? Because you have the whole distribution. So you're only going to get the sigma here. Okay, so that's important to know. Okay. Okay, so these two parameters, so here the standard deviation was 1, right? So this, I'm going to write this down. This probability distribution has a mean of 2 and a standard deviation of 1. Now that's not by accident. I mean, like, I literally built it that way. So we get nice, neat numbers. You don't normally get nice, neat numbers there. Flipping around the language a bit, we talk about, given a probability distribution, the expected value, okay? Now, expected value is literally the same thing as the mean. There is no difference between the two. The mean of the standard or the probability distribution is the same as the expected value. Okay, so there's a slight problem here because this is like, if you were to do the procedure, what is the value that you would expect to get for the random variable? Okay, well, if you have the probability distribution for like 5 births, you would expect, or that the mean that you get for that probability distribution is 2.5 girls. No family has 2.5 girls, so you cannot expect that to be the value of the random variable. So what we do is we kind of use that to make a judgment, and when we report out, we would say that we would expect the family to have 2 girls, maybe 3. Because we know it can't have 2.5. So you have to kind of make an adjustment in language there when reporting that out. But you're noticing that you're making an inference here now. So what you're doing is you're taking the probability distribution and you're able to calculate the mean of that distribution and make an inference. Inferentially, I would expect this to result at 2.5. Now, you can apply the range rule of thumb to that, okay? So in our example here, we had a mean of 2 and a standard deviation of 1. So what I would expect the result of this procedure to be 2. And in fact, it's the most common result in that table. So if you go back and look at that table, the most likely result is 2. It has a 37.5% chance of happening. It's more likely than any other result. However, the that gives me the idea of like a single expected value. So what I can do is I can use my range rule of thumb. I can say that usually values are going to be within 2 standard deviations of the mean. So if the mean is 2, I would expect my values to be between 0 to minus 2 times the standard deviation, or 2 plus 2 times the standard deviation, and 4. And in fact, all of the values in this probability distribution are between 0 and 4 inclusively. It's kind of nice that that happens. So, like, getting a 5 or a -1 from this probability distribution would be unusual. It's not an outlier, it's unusual. Okay, so I can make an inference. Given the distribution, I can infer that I would expect the values to be between 0 and 4. This is going to be huge later on, right? Because this is how you're going to be able to say, oh, given this statistical sample, I expect that the mean of this population is going to be between X number and Y number, which is what we're going to call a confidence interval. So this is the beginning of inferential statistics here. All right, so that's like a generic probability distribution. On the discrete side of things, we have two named distributions that I tend to teach. Now, not every course teaches the same probability distributions. Almost every beginning statistics course does teach the binomial distribution, and usually one other as a discrete form. And usually they pick one of two. They either pick Poisson or they pick geometric. Now, I go with Poisson because it's ease of calculation. The AP exam uses the geometric. Poisson is the probability of having a certain number, an event occur a certain number of times on an interval. The geometric probability is the distribution of how many times you have to do a procedure before you get a successful trial. I like Poisson because of ease of calculation for teaching purposes, but if you want to do a deep dive later on geometric, please by all means do that. That is what is taught in the AP course as the second probability distribution. Okay, so let's talk binomial. The binomial distribution has certain characteristics. It has a fixed number of trials. So you're going to do a procedure a fixed number of times. 10 times, 100 times, but it's going to be finite, right? And we're going to call that n. N is going to be the fixed number of trials. Now, there's certain characteristics that those trials have to have. They have to be independent, okay? So the probability, so if you're thinking about this, like there's a connection to like what we did with probability here, right? Because independent means that the probability of A given B is equal to the probability of A, right? There is no sense that the given B had anything to do with the next trial, right? So the probability of one trial does not affect the probability of the next one. And that the trial has two possible outcomes. So the two outcomes are what we call success and failure. Now, these words are weird, okay? Because like if you think about this, you can get into odd situations where like somebody is trying to figure out the probability that you're going to die today, and actually dying would be the successful outcome. Okay, so that's a weird thing, but you usually call one of them success and you call one of them failure. Now, we use the letter P to indicate the probability of getting a success on a particular trial. And we use Q to indicate, which is the same as 1 minus P, that we have a failure on a given trial. And a trial will either succeed or it will fail. It cannot do both. This is why these are complements. Q has to be 1 minus P. Okay? So the random variable X is going to describe the number of successful trials out of n trials. Okay, so that's where these are. So there's four numbers that are being juggled here. N is the number of trials, P is the probability of success, Q, which is 1 minus P, is the probability of failure, and X is the number of successes that I get. That's what we're counting as the random variable. And we just kind of walked through all that notation. Okay, so I give an example here. Oops. Oops, I'm moving that all over crazy because I got myself in the wrong screen. All right, there we go. We give an example here, so I'm going to clear some of this out, and we're going to do an example. In our example, we're talking about Instagram use, okay? And we're going to say that if you grab an adult at random, the probability that they're going to know how to use Instagram is 85%. Now, that might be high or low. I don't know. I'm probably making that number up somewhere along the line here. So what we're going to do is we're going to grab 5 adults at random. Okay. Now, from that 85, I know that Q has to be 1 minus 85, which is 15%. So really, in order to do a binomial exploration, you really only need the N and the P. The Q you get for free. Okay, so let's say I want to know the probability that if I grabbed 5, what is the probability that I get exactly 3 adults that know how to do this? Okay, so there is a formula for this, and it seems kind of daunting at first, that the probability that x is equal to x, right? That's weird to say, is npx times little p, so this is a big P, right? This is the permutation P, little p to the x times little q to the n minus x. Now, that seems like an awful formula. Okay, so let's break that down a little bit and see if we can understand a bit of what's going on here. This part is the easy part to understand. Okay, so this is saying I'm going to have x successes, right? So that means multiplication rule. I get chance of that happening, x successes, is 0.85 times 0.85 times 0.85 x times, which means I'm going to have n minus x failures, right? So that's the 0.5, 0.15, 0.15, 0.15, n minus x times. And I multiply that all together, and that's the probability of having an outcome that has x successes and n minus x failures. Kind of. The problem is that that is going to tell you the probability if you order the successes and failures one way. Okay, so this is the problem. Like I could have, let's say in my trial of 5, I could have success, 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 fail, fail, right? And this would give me the probability of that happening. But I could have success, 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 or fail, success, fail. This would give me the probability of that happening. But I have a probability of either of these happening. So how many different combinations do I have here? Well, what I'm going to do is out of 5, right, 3 of them have to be successes. So how many different ways can I order 3 things given 5 slots? So this is why I get the nx. So if I were to list out all of these, there would be 5 permute 3 of these possibilities. Okay? So that's where this comes from. Now, this is a bit of a deep dive into this. Your kids really don't need to know this, and in fact, they don't even need to know this formula. And most of them, by the time they get to this, don't. Okay? You could have them do some by hand. That's fun, but it's not necessary. Because one of the nice things about when we live and all of this is that all of this is built into the calculator. So if I have a binomial situation where I have 5 trials and the probability of success is 85%, and I want to know the probability of x is equal to 3, I can have the calculator do the work from here. So I go into the calculator. It's actually all built in there. Turn it on. Go back to my main screen. And what I'm going to look for is a distribution, and that's the second on the vars key here. So I go second vars. If you look a little ways down, you're going to get binomial. And this is the binomial probability distribution function and the probability binomial cumulative distribution function. Usually for binomial, we don't worry about the CDF. We'll see how we use that with Poisson in a minute. But binomial, we tend to use the PDF. So it actually brings me up a wizard that gives me these things. I'm doing 5 trials. The probability of success is 0.85. The X value that I'm looking for is 3. I go paste back to the main screen. And literally what this is this is how you used to have to type it all into the calculator. So it just uses the wizard to create the command that the calculator would use. If you have students that have an old calculator, this is how they would have to type it in. And you hit enter. And that gives me 13.81, which means that if I had grabbed 5 adults at random with an 85% chance that each one of them is going to know how to use Instagram, I have a 13.8% chance of grabbing a group of 3 Instagram using adults and 2 who are not. 13.8% of the time. Okay. Now, you could go and you could build the entire probability distribution this way, right? So, like the probability distribution that I want here would have X, right? With possible outcomes 0, 1, 2, 3, 4, and 5 adults with associated probabilities, and the 3 being 0.1382. Okay, now that's a lot of work to like build it all this way, one probability at a time. So what I'm going to do is I'm going to automate that a little bit. Okay, and I'm going to go into my stat and I'm going to build a table and I'm going to clear everything that's in here out because this is old junk that I don't need because I was using it before. Okay, so I put the possible outcomes into list 1. All right, then I leave there. I go back to the main screen and I say, okay, go second vars, grab my binomial PDF, right? 5 trials, probability of success is 0.85. And now, instead of just putting a particular X value in there, I put a list of X values. I put in L1. Now I paste, right? I'm going to hit that once because I'm going to use this store key down here. I'm going to store. And I'm going to store the results of that into L2. This is going to produce a list, and I want it to drop that list into L2. So I hit enter. It produced the list. If I go stat, edit, and there's all the probability distribution. It's all there. I can look at the whole thing. So this is the binomial distribution for 5 trials with a probability of 0.85 chance of success. Now, where do the kids goof it up? They goof it up right there because that looks like 7.6, but that's 7.6 times 10 to the negative 5th, which means it's really, really, really not likely that you're going to grab 5 adults and find that none of them know how to use Instagram, right? In fact, the most likely result here, given our model, is that all 5 of them will. 44.3% of the time, all 5 of them will. So, kind of working that out. Something that would be nice to know is like, what is the expected value, right? And this is something that happens. So each probability distribution is going to yield 2 parameters. Right, so I'm going to scroll down because we just did all that. It's going to yield a, what do you call it? A mean and an expected standard deviation. Now, given that we just did this would be really easy because I could go stat calc the one variable statistics, run it on list 1 and list 2, and it tells me that the mean is 4.25. So the mean or the expected value of this probability distribution is 4.25. And the standard deviation of this is 0.7984. Okay, but that seems like a lot of work to get the mean and the standard deviation from N and P. Okay, so I took away the 1.5 here from that. All right, so you can get those straight off. When you're working in the binomial distribution, the expected value, or the mean of the distribution, is literally just n times p. 5 times 0, or 0.085. And if you think about this long enough and hard enough, that's going to make like an intuitive sense. 5 times 0.85, and that gives me the 4.25, which is precisely what doing the what do you call it? Weighted mean using the calculator gave me anyway. So what does that mean? That means like if I grab 5 adults in this situation, I would expect between 4 or 5 of them to know how to use Instagram, more likely 4 than 5, because 4.25 is closer to 4 than 5. Okay, so standard deviation here, we have a formula for that. And you can literally find the standard deviation by taking the square root of the mean, which is NP, times Q. So in this case, this is going to be square root 5 times 0.85 times 0.15, and that's going to give me that, there's the same number, 0.7984, which is the standard deviation I expected here. Okay, so what do we got going on there? This is where you can like start drawing inferences, right? Because remember, like your range rule of thumb says you should be within 2 standard deviations of the mean. So if I take 4.25, 4.25 and subtract 2 times 0.7984, right? That's going to give me 2.65. And if I do the same calculation, but I add the 2 standard deviations, that's going to give me 5.85, right? Which means that if I did this experiment and I grabbed 5 adults and I say, hey, how many of you are like able to use Instagram? I should expect that between 2.65 and 5.85 of them could, which means it's really 3, 4, or 5 of them would. If I actually grabbed 5 adults and found that 0, 1, or 2 could, only that many could, then there's something unusual about that sample. And I should start looking deeper, right? So the inference says that I should expect the usual sample should give me 3, 4, or 5 adults knowing how to use Instagram. So I'm able to actually start drawing an inference there from a sample, which is kind of neat. All right, so that's binomial. All right, so let's look at Poisson. Now, Poisson is a little bit different situation. It's a funny word too. All right, so Poisson. All right, Poisson is French. It means fish. There's my little fish. It has nothing to do with fish. It's just a guy's name. But if you have an astute student in your class who's taken French, they're going to know that that means fish. But it has nothing to do with the math. All right. So just a guy named Fish discovered it, but he was French. All right, so here we go. Poisson is a little bit different. Here you have a fixed interval. Okay, it starts, it ends. Okay, so a fixed interval. It's usually time. Oftentimes it's time. It can be other things, but it's usually time. We have occurrences, right? So occurrences happen at random. They're random. So each, that's part of my consideration there. The occurrences are independent. So once one occurs does not mean that the next one's going to occur. So one occurrence will not cause another one to happen. They're uniformly distributed. So they're not going to bunch up. Okay. And the last thing is that the random variable here is going to be the number of occurrences over the interval. Now, I'm going to give us an example here a little bit later on, and I'm actually going to violate number 3 with my example because it's really hard to come up with a Poisson example. And my violation is that I'm going to talk about something that's not uniformly distributed, namely hurricanes, because they do tend to bunch up. Okay. But we'll get into why this model will still hold, because usually hurricanes happen within a season. So what we'll do is we'll assume that that season is the interval, and hurricanes tend to not bunch up within the season, but they tend to bunch up like within the year. So we're going to be okay. So if you're wondering if I'm violating number 3 with my example, the answer is yes, I am, but it's still going to work because we're just going to have it be over the season and not the year. All right, so I'm going to let that go. All right, so where you had n and p and q in binomial and Poisson, you only have one. You have a thing called lambda. Looks like an upside down y. And lambda is the expected number of occurrences on the interval. All right, so that's actually the only knob we have, is once you know the expected number of occurrences on the interval, then you can start talking about Poisson distributions. So how does this work? All right. So, excuse me. I have an example here where we're going to say in the Atlantic Ocean, in the past 100 years, there have been 530 hurricanes. Woohoo. Okay. Which means that we should expect 530 over 100, or 5.3 hurricanes per year in the Atlantic. Now, fact of the matter is that this is actually one of the evidences that we point to for climate change, because the lambda in the Atlantic Ocean is actually increasing. So it's not a constant. But we can keep pretending like it's not happening. But right now, we got other fish to fry. So this is lambda. Let's say lambda is a constant. It's 5.3. All right. Now, the Poisson distribution cannot be given as a table, and we'll get into in a minute why that is, but it can be given as a formula. You're not going to derive this formula because it's way too complicated. This, in fact, is the Poisson distribution formula. Okay, so the probability that we have x number of hurricanes is lambda to the power of x minus e to the negative lambda over x factorial. That's nuts. At this level of statistics in high school, nobody goes into explaining why that works. Okay, but we're there. Now, here's the problem. You can't build this as a table, because what's the maximum number of hurricanes we can have in a year? Well, the minimum is 0. We can't have -7 hurricanes. But hey, if we could have 14, we can add one more. There could be 15. There could be 16. There could actually be 1 million hurricanes in a year. It is highly unlikely that's going to happen, and the probability in the distribution is going to be really, 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 really close. And I tell the kids that it's what we call DCTZ, which is mathematical for damn close to zero, but it's still possible. Not likely. The probability is dang close to zero, but that's what we got. All right, so you cannot build a table because you cannot have, every time you get to the highest number, you just add 1, and then you're at the next highest number. So we're not going to have the kids feed this in there. I mean, you could have them do it by hand. It would be fun. It's an exercise. And again, the calculator comes to save the day. If I look under the distribution second vars, I scroll down a little bit here. Lo and behold, I have Poisson PDF. Now at this point, they should have been used to using the binomial PDF, so having the Poisson PDF should not feel all that wonky. When I do this, I get, hey, there's lambda, 5.3, x value. Let's say I want to know the probability there's going to be 4 hurricanes this year. So I put in 4, and I paste, and I hit enter, and it's 16.4%. So if on average there's 5.3 hurricanes over a year's span, we can expect the probability of having 4 hurricanes in the Atlantic this year is 16.4%. Okay, it's pretty simple, right? This gets me into the idea of ranges, okay? So let's say I want to know the probability that I will have less than or equal to 3 hurricanes this year. And this seems like an odd thing to ask until you realize something that happens a little bit later on here. So let's try to figure this out. This is where instead of using the PDF, the probability distribution function, I'm going to use the CDF, the cumulative probability distribution function. Cumulative means up to and including 3. So I go second vars, I go down to binomial or Poisson CDF, and I'm going to accumulate up to and including 3. So my lambda is still 5.3. My x value is now 3. And the probability of getting everything up to and including 3 hurricanes, so this would be 0 hurricanes, 1 hurricane, 2 hurricanes, or 3 hurricanes, is 22.5%. Okay. Now, why is this important? Because calculating this, I could actually do the chart and come up with the probability for 0, and add that to the probability of 1, and add that to the probability of 2, and add that to the probability of 3, and I could come up with this answer. But what if I want the probability that the number of hurricanes is going to exceed 3? Well, that would be the probability of 4 plus the probability of 5 plus the probability of 6 plus the probability of 1,000,000 plus the probability of, oh, wait, I can't get all of them because I can keep going off to infinity here. But here's the trick. These are complements. So this is why we learned that back there. Complements. And the probability of having more than 3 hurricanes is actually 1 minus the probability of having less than or equal to 3 hurricanes. And there's the trick. So if I take 1 minus this answer, I now have the probability of getting more than 3 hurricanes, which is 77.5% chance. And I don't need to know all those little probabilities that are dang close to 0 way up there. So this is a neat little trick, okay? Now, why Poisson has an ease of calculation comes to when we try to draw inferences. Because the way we designed Poisson, oops, that's not liking me. There we go. Oh. O-N. The way we designed Poisson is that lambda was the expected value. The expected number of hurricanes was 5.3, which means that that is the mean. So in Poisson, you can turn that around. The mean, or the expected value, is lambda. Now, a neat little fact here is that the standard deviation, and if you go through all the calculations, it works out, it's just the square root of lambda. Whoa, makes it so easy. So if my lambda was 5.3, my mean is just 5.3. And the standard deviation here is going to be the square root of 5.3. Okay, so let's figure out what that is. Let's take the square root of 5.3, which gives me approximately 2.30. Now, that means in an average year, right, if I use my range rule of thumb, if I take 5.3 and subtract 2 times 2.30, I get 0.7. And on the other end, if I take 5.3 and I add 2.30, I get 9.9, which means that I would expect between 0.7 and 9.9 Atlantic Ocean hurricanes in a given year, which means if I had a year with no hurricanes, that would be weird. If I had a group with 10 or more hurricanes, that also would be unusual. Now, start thinking through names A, B, C, D, E, F, G, H, I, J. J, right? So like Katrina, if this was true, Katrina would have been a weird hurricane, right? So would have Rita. So these numbers can't possibly be right for current day, okay? And what we're actually finding, and which gets me to the whole climate change thing, is that year after year, the Atlantic Ocean, we're actually getting further into the alphabet, which is one of the evidences that like Greta Thunberg and folks are like pointing to and going, the world's changing, okay? And this is how scientists, one of the ways that scientists can get at this is they could use Poisson using a look back at the data, grab the interval of what should be happening, and then if we start exceeding that interval on a regular basis, we can draw the inference that there is actually climate change, okay? And that's like a really powerful tool and really relevant to our world right now. We do this intuitively. Okay, we do look backs and then we look and see if things are getting better or worse, right? So like the intuitive thought here is like, all right, as I'm recording this, we're in the middle of COVID, right? And people are talking about like number of cases per day. Okay, and you have this idea, like looking back over the past couple of weeks, how many cases per day do you expect to be happening? And you can come up with an interval for what you would expect to happen tomorrow or the next day. And if we exceed that interval, then something has changed. Either things are getting worse, we're exceeding that interval to the positive side, and either that could be accounted for by an increase in testing, or it could be accounted for by people's increase in mobility, less adherence to measures like social distancing and mask wearing, whatever, would all be things that we call on the positive side. Or you could say, ooh, wait, we're having fewer occurrences, which means we might have had a drop off in testing, or we might have had, people actually in doing social distancing better, or we might have, managed like, hey, we found some weird thing that if I eat this fruit, that you're no longer having this thing. Now, eating a fruit's not likely the answer, but a vaccine would definitely move us to the left side of the expected interval. So this is where like we make an inference and then we test that inference, yeah, against statistical sampling. And if the inference lines, or if the, what do you call it, the statistical sampling doesn't line up with our inference, we reject the hypothesis, which is where we're going down the road here into hypothesis testing. And we say that we don't either do or don't support a claim basing on whether or not we reject that hypothesis. So probability distributions are the beginning of inferential statistics here. The next asynchronous thing you're going to get is on non-discrete, because this is really easy to start with discrete things where you have countable or finite realities. So binomial is both countable and finite. Poisson is countable but not finite, right? So that's where you get that distinction there. If you did the geometric one, it is also countable but not finite. Like it's when do you get the first success? So that's going to be countable but not finite. But many things that we measure are continuous, and that's going to bring us into the normal distribution and the t-distribution, which are going to be examples. Uniform distribution is also continuous, where we're going to measure things that you can have spaces in between the spaces. One of the problems that the students have is actually understanding when am I doing Poisson and when am I doing binomial, right? So at some point I tend to build a table for them and have them kind of hack out which one's which. Binomial is you have fixed trials. Poisson, you have a fixed interval. Here you have a probability of success and failure. Here you have, so this is n, you have a expected number of occurrences. Usually here you only have one knob, here you have two knobs, n and p. So what I would normally do if I'm teaching this is give a set of problem sets that have both binomial and Poisson problems and have them like work out, okay, is this binomial or is this Poisson? And then answer questions about it as we go along. All right, so there you go. That's the 5th asynchronous session. And we'll do 2 more asynchronous ones, and then we'll meet again in August, and then we'll be done. Woohoo! There you go. Have a great summer.